Welcome. In this lecture I will discuss the development and the current status of MPR 9998. This is the Dutch guideline for practice to assess buildings under earthquake load in Groningen. The MPR establishes the principles, rules of application and assessment measures for the assessment of reliability of structures under seismic loading. The MPR is being developed by the Dutch Normalization Institute NEN to design and assess buildings under seismic load in Groningen. The MPR will be updated from time to time in order to incorporate the latest insights with respect to hazard, fragility and risk. In the MPR, a performance-based assessment of structures under seismic loading takes place. The specification of the target reliability level, as well as the calculation of the actual reliability, are key points. Target values for reliability may be related to aspects of human safety, as well as to economic optimization. The graph shows the safety level on the horizontal axis and the costs on the vertical axis. As can be seen from the graph, a cost-optimal safety level balances between the building costs and the failure costs. Here, the failure costs should be understood being the probability of failure times the damage. The lower boundary of the safety level follows from notions such as individual risk. This system has been elaborated in Eurocode EN 1990 and the corresponding Dutch National Annex for new structures and in NEN 8700 for existing ones. In earthquake engineering, a convenient approach is to make a subdivision into 5 damage states called DS1 to DS5, ranging from small damage to full collapse. For life safety, only DS4 and DS5 are of importance. After the passing of the DS4 limit, there is quite an amount of economic damage. The structure is usually beyond repair, but the number of casualties is believed to be small. In the case of passing the DS5 limit, the number of casualties may be large, depending on the type and use of the structure. In the MPR, the focus lies on 3 limit states. First, near collapse, NC, on the verge of global collapse. Second, significant damage, SD, damaged but stable, no collapse according to Eurocode 8 Part 1. And third, damage limitation, DL, the structure needs some repair. The safety criteria for human life usually dominate for existing structures. In the Dutch Code for Existing Structures NEN 8700, the limit value for the individual risk has been taken as 10 to the power minus 5. This is the maximum acceptable probability that a person dies in 1 year as a result of a collapsing structure. So, this means that the actual probability, the annual probability that an individual dies as a result of structural failure due to an earthquake should be smaller than 10 to the power minus 5. Based on an individual risk target of 10 to the power minus 5, the annual target collapse probabilities can be derived for structures in DS5 for the 3 consequence classes from EN 1990. In the blue blocks, the annual target collapse probabilities are shown. These are the starting point for the structural reliability calculation. Suppose FSA is the probability density function of the annual maximum hazard at the location of the structure, and capital FR is the fragility function of the structure under consideration for damage state 5. Then, the annual probability of collapse of the structure, PF, under earthquake load can be calculated as can be seen in the graph. The degree of overlapping determines how large the failure probability is. This requirement can be translated in a load and resistance factor design procedure. Here we can see the partial load factors on the load side, the so-called importance factors, and resistance factors related to the near collapse limit state. In seismic design, we define demands on our structures. Structural members have strength and displacement capacities, and these are compared with strength and displacement demands. Both demands and capacities have a probability distribution. If we know the demand and capacity probabilities, it's possible to calculate the probability of failure. Departing from a certain probability of failure, the design values for demand and capacity can be calibrated to be used in practice by the structural engineer. Finally, the structural engineer can then work with his load and resistance factor design to assess the safety of the structure under seismic load. Based on the target level for the individual risk in this way, a reliability-based method is developed for the design of new structures and assessment of existing structures under seismic load. Seismic demands follow from the probabilistic seismic hazard analysis. One of the representations is a peak ground acceleration map for an annual exceedance probability of 1 divided by 475. In the MPR, an ideal reference elastic site is chosen. Translation into return periods that are needed to satisfy the individual risk level of 10 to the power minus 5 is done via importance factors. Translation into acceleration levels for real soil conditions is done via the formulas for the spectrum. For the analysis of structures under seismic loading, the MPR provides linear and nonlinear methods with corresponding safety formats that lead to an individual risk level of 10 to the power minus 5. The linear methods include the lateral force method and the modal response method that can be applied to new structures under the condition that the detailing is done according to EN 1998. The nonlinear methods are better suited for existing structures. The nonlinear time history analysis gives a good insight in real failure mechanisms. Some regulations and requirements for the application of this method are provided in Annex F of the MPR together with a safety format. Summarizing, you now have an insight in what the seismic engineer needs to be able to make a seismic assessment. We discussed the way how to define target reliability levels for seismic assessment. In the MPR, the target reliability is based on the individual risk. This is translated into return periods and importance factors for the seismic loads and into safety formats for the analysis methods. Thank you.